And let's ask the first question. How does the stability of this pattern, this initial pattern, depend on the parameters, in particular on the dipole orientation of this intermediate system? Now, what would be the naive answer here? The intuitive answer. The intuitive answer would be the following. Okay, I have this blue and the red, and then I have this type of spin exchange with them, which will gives me everything, and then at the end, I will get like 50-50, right? Completely mixed after some time. So when is this going to happen in the easiest way? When this interleg exchange is the largest. And this happens to be when the dipoles are oriented like this, when this angle is 0. Yes. So this naive answer would be the pattern is most unstable with theta is 0. So when the interleg interaction is maximum. But this happens to be wrong, right? And why this is like this? Okay, let's take this model that I was saying to you, but instead of following everything, I will just follow the defects. So I will follow the red particles in the blue leg or the blue particles in the red leg. I do this trick, which is called the Holstein-Riemann function. Yeah? And then I transform these defects into hard-ball Gaussians. So I start with the vacuum. I have nothing, I have no defect. Everything is blue up, everything is red below. But then I have the interleg of it, which is taken to a pair creation in this language. So I create a boson, which I call here the boson A and the boson B. You know, that is correlated pair creation, similar, for example, to two-mode squeezing. For example, actually, this is actually one way of creating squeezing, and Maria thinks that this. Now, the other process, which is this intraleg exchange, leads to this leg hopping along the legs of this hardcore process. So I have these two processes, and now I will forget the hardcore nature, assuming that I have a dilute gas of these excitations, of these defects. And then I move to momentum space. And here I have the whole physics. So I have this intraleg force. Yes, so which I characterize with this back dispersion epsilon, which is nothing else than the Fourier transform of the diagonal interaction along the legs. And then I have this correlated interleg pair creation, which is here at this rate, which happens to be just the Fourier transform of the interleg diagonal interaction. So it has a given momentum dependence, which depends in a non-trivial way with the spacing and with the So now we will go with information in order to see the quasi-particle spectrum and see the stability analysis. And then you see that if what is in the side of the square root becomes negative, I have instability. Now, when is this the most unstable situation? The most unstable situation is epsilon, so the band dispersion is 0 for every momentum. Because in that case, I will get a negative factor for every momentum. Yes, inside the square root, and therefore you will have imaginary for every. Okay. But I told you that this is the Fourier transform, essentially the Fourier transform of the intraleg interaction. So, ergo, the system is massively unstable not when you have the maximal interleg interaction, but when you have the minimal intraleg interaction. So, and this is actually possible in the leg. I just tilted the angle such that you hit what is called the magic angle, and which you kill the intraleg interaction. So in this graph, what you see there, just follow the white dash curve. Below this white dash curve, you have instability, and over that you have volume of stability. So you see that this is maximally unstable at this rational you have there, which happens to be the point at which you have 0 intraleg interaction. But this is the first question. Now, the second question is what happens in the long term? What happens when I go beyond this initial volume? What happens? Now, what would be the naive answer? The naive answer would be, okay, when I move these legs apart, the interleg interaction becomes weaker and weaker and weaker and weaker. And actually, it becomes weaker with 1 over delta squared. But you integrate over one direction, the diameter of the direction is q. Yes, so to integrate in one direction, you get the square. Now, this means that naively, I would expect, okay, for any distance, I have the same physics, but just I stretch the time scale by delta square, right? So if I am twice more separated, the time scale will be 4 times bigger, let's say. But this happens to be also, right, in this case. So what you would expect is something like this. This is the full counting statistics of the number of spin excitations. So let's say of red particles of the blue length or blue particles of the red length. So initially, you have not for no for the children.
Maybe like this is fine.
Is better? Yeah. So okay. So the full counting statistics is the same counting the number of defects. So initially, I have no defect with probability of 100%. So this is a sort of histogram, right? Now, so in the short term, what I have is of exponential histogram, which is actually directly related to the exponential creation of pairs that they have this dynamic stability. But then, when I start to have to see the hardcore nature of the bosons, then I start to go from this exponential to this final distribution, which is equilibrium, which is a Gaussian, which is just simply a pure combinatorics. At the end, the probability of the half, like, with a given number of particles, is purely given by the number of particles, not where they are, but just how many states they have with a given number of excitation. And this is combinatorics. Yes, I can see these binomial factors there, and it gives you this exponential. So this is what you would expect. And then naively you would expect, okay, I take my this farther and farther and further away, that this will stretch the time scale for a one, but it will get always the same. This is wrong, because what you get is more something like this. So first, this is the sort of diagram. Yes. So you have in the y-axis you have the separation, the legs, in the x-axis you have the pattern of orientation. The picture that I was showing in the previous slide is only including this dark blue region, which I call here the body, which is surprised the way given by this Google analysis. If you are at large distances, you are getting in the region which you call the quasi-local region, which is this last picture here at the bottom, in which basically the initial pattern is stable. Right? So, and this is not a question of that I didn't wait enough. Yes. If I wait this time scale of delta square, I will still see this. I will have to wait for an enormously long time, exponentially long time, to see something else. Because at the end of the day, in this problem, you should end in the equilibrium that I was telling. And this can take huge amounts of time, completely unrealistic for experiments. Now, the interesting is that you can have this type of partially relaxed situation, which is there, which is these two graphs which are in the middle, at which you see a large probability to be still localized, which is this peak at 0, which is over there, which means that there is no excitation. I have the original, I am in the original state. Yes, but then I have this Gaussian region, so I want to binodal distribution. So this means that in an experiment with 30% probability to say I will stay in my original state, and in some other experiments I will be already relaxed. Yes. So this is pointing to the fact that we did not study this yet, but this pointed to the fact that the many variable states have very different degrees of velocity, and your initial state basically projects into different families with different degrees of velocity. Okay, so this is the first scenario that I wanted to discuss. And the second one is even a simpler scenario. So there's no divergent interaction. It's just both of others. But we will see that there is a sort of surprising link between dynamics and topology in the standard systems induced by interactions. So this is again motivated by very recent experiments performed on NPQ, the group of Monica Edelsburger, in which they have bosons, no bipolar bosons, so just with separate interactions, in an optical ladder with an initial density growth. So they have doubly occupied, empty, doubly occupied, empty random, doubly occupied, empty random. So like this. Here the key parameters are the leg hopping, which I call the J parallel, and the run hopping, which I call J parallel. So in the hardcore regime, this is everything I will have. I will have a U very large, such that I can forget completely that I can have 2 particles per side. And then is the question that was at the beginning. I have this initial condition, which is the wave, I relax it, what happens? Right. In this paper, there is like several things, but one thing which is pretty revealing is the so-called random density formation. So which basically is you just take one run, see how many particles you have, and then check the relation between the different runs. So the density formation, the numbers between the different runs. And this is very illuminated if I look at this, because when you have the 2 legs are disconnected, so there is no hopping along the runs. This problem is very integral, and the expansions of these correlations is ballistic. So you basically see that these correlations are there. In the x-axis is the spacing in the sides, and in the y-axis is time. There is this type of cone which is propagating, and this is the ballistic expansion, basically of these correlations, which is they are negative, and this is after the rest expansion which propagates with a velocity given by the leg cognitive power. Now, in that paper, they explain what happens if you move now to J parallel equal to J parallel, so the sort of symmetric configuration. And they observe that these correlations go from a ballistic to a diffusive evolution, right? And indeed, if you have a look to what happens if you go forward from there to eta equal to 2, then you get subdiffusing and inventory localized, and this during the time scales typical of the experiments that they have.
The special function squared is positive, so the right-hand side is negative. On the colored bar, you will still have some positive values.
Yes, but only in 0. Only in 0.
Oh, I see.
That is a sort of, we should remove the 0. Yes, this is true. Yeah. Okay. So, nicely, now you will say, okay, I make now this ratio, it's a bigger and bigger, and then I will get more and more and more localized. But this is again wrong, right? It's again not what happens, because you happen to have this something like this. Yeah, so you have this type of scatter around density relations, and after the overall expansion. And the reason for this is can be understood if you have a look to the possible particle states there. So you have 2 particles, 0 particles, or 1 particle, which may be in symmetrical or asymmetric combination, which have different rank energies given by the hopping along the rank. Now, you can have the leg hopping to results in the creation of pairs of signal difference. So what it means is that I can take 2 of these and then create this, right? So I take 2 and then create a difference, which is actually either plus or minus. You can create plus or minus because of sort of quantum physics. Now these guys can now move, right, resonantly in the system. So this creation is of course very non-resonant, just because it goes with an energy generated with plus minus J bar, and the J bar is larger than J bar, this is called non-resonant. But once you have created, yes, they can now move resonantly. And what you get is a sort of string of states of ranks which are fleet staggering with respect to the original one. This is actually what is behind the staggering that you have for the one which is mathematical. Now, even more interestingly is what happens due to the finite on-site interactions. Due to the super strange factor was discussed before in the talk of the videos. Then you get this additional Hamiltonian, there are several types there. can play an important role, but the important one is the middle one, which is this J parallel, the middle one, this extra terms, which is nothing else than collision and resisted hopping along the diagonals. So basically, a particle can now hop along the diagonal if it has neighbors. Yes, only if it has neighbors. And this means that you have now two ways of swapping position between a single different. Single different is just a singly occupied part, and a double occupied part. You can either do it directly or via this collision resisted hopping diagonal convention. So this means that now you have a look to how plus minus swap with 2. You have a different hopping rate for plus and for minus. Plus hops with a larger hopping rate, and minus hops with a smaller hopping rate. But both of them hop equally, mainly with J parallel, with respect when they hop with the 0. So as a matter of fact, this means that if I have a different plus or minus, yes, and I have some sort of effect in the initial distribution, and actually this happens in the experiments of Monica. So you have some possibility to have, for example, in this case, a singly occupied random choose of an empty round, for example, there. Now, when it swap positions, there it swap with some uniform rate. So it can move in this way in the left. But now we hop here with some other, and here with the same as the previous one, and therefore J2 and so on. So what you recover is that now this single duplex move in an SSH chain. So with J1, J2, J1, J2, J1, J2, but is a peculiar organization of this without any external potential, just purely emerging from interactions. So you can follow with me, you start there, you get blue, red, blue, red, blue, blue, red, blue, red, blue, red. Yes, so you get a defect there in the staggering. And this means that you have an interface between SSH change with opposite of time. And as a result of that, this system is characterized by a localized zero-energy edge instead, a sort of interface which is given in the A's of lattice and is localized with a localization there, as you can see one way with the ratio of J21. Now, since the initial defect is clear construction living at the interface, this means that this initial defect it has a large superposition with it. And as a result of this, the initial defects project with large probability to this localized state, and you get this type of topological localization of this type of defects. Moreover, if now you take, for example, plus between two doubles like this one, and not a minus like before, and you have the staggering is now inverted, so the J1 is larger than J2. In this case, you have still an edge state, but the edge state is given in the wrong sublattice, it's given in the B sublattice instead of the A sublattice, which is the original one where the defect is. And therefore, it does not affect the defect. But you get additional localized states there. And these additional localized states basically are separated by an edge, which is twice the same that they're putting there. And then what you have is a projection of this into this superposition. And therefore, you get an oscillation between the A and B sublattices with some frequency. So basically, either topologically or energetically, the same or topologically, what you get is that these defects are to a very large extent localized due to this effective peculiar SSH change that you realize without any external modification. So this is all I wanted to say, right? About these two scenarios, in particular this second scenario that we discussed here about this funny link between topology and dynamics and scalar systems. So I would like to finish thanking the people who collaborated, particularly Gustavo in Hanover, a very talented postdoc, and David and Maria in Chile, and Thomas Witteski in Oman. Thank you very much.
Thank you very much for the meeting. So the room is open for questions.
So Luis, I have two questions regarding the first part. So in particular, your initial state is a unit density initial state, right? The molecules.
Yes.
That is not what they have at Gila, right? So they have a TJ model, so which is the effect of empty sites.
This is actually a very good question. We addressed this not in this paper, but in the previous one that we developed in the planes. And indeed, for the dynamics, it does not affect so much for example, negation of momentum pattern that we observe. Yes. So basically, but in this case, it's not EJ. Yes, because in the case of GLAD, basically you assume a much weaker or basically no lattice whatsoever. Right? Whereas in this case, we assume a relatively strong lattice. In the case of GLAD, they have two planes without any lattice.
I have a second question regarding the relaxation dynamics. So how the time that you extract is compared with the lifetime of the molecules?
Yeah. So more than with the lifetime is the most important one is the coherence time of the rotational. And this has been shown by Simon Cornish that you can get up to seconds. In this case, this will be of the order of 1,000 to 2,000 photons.
There. Oh. Speak out.
We were trying to reduce the volume of the mics. Please, thank you very much. The defect localized. Usually, I use the defects that you want, which you find wherever you want.
Yeah.
Is it because you have to find a change? Where do you fix the change?
So actually, in this case, this topological localization is due to the defect in the staggering. Right. So basically, you get an edge between two chains. This defect never sees anything else. And actually, this is important because you will have more than one, so to say. And this is somehow in the local neighborhood where this is. So you will have one defect here, another defect here, another defect here, right? All of them will have the same partial localization and partial extension, right? And it is quite important, and I have time to discuss about this, but when they extend, they actually repel each other, so they form like boxes, right? So within these boxes, you have extension and you have localization. But for the localization, you don't need to see the edges over there, you just need to see that there is an edge that it is effective as a switch model.
Is there any more questions? No? So if not, let's thank the speaker again. And we'll reconvene in half an hour.